Good afternoon, Project Haystack, and to all the Haystack community, and to everyone attending the Haystack Connect conference for 2021. Thank you for your attendance. Thank you for all the contributions from the presenters. I hope everyone's been enjoying the conference, and I know we're at getting towards the very end of the Haystack Connect conference for 2021. My name is Richard McElhinney. I'm the Chief Software Architect at Conserve in Melbourne, Australia. So hello from down under. I'm sorry I can't join you live this time. Unfortunately, the timing hasn't quite worked out for me. Today, I'm going to dive right into it. I'm talking about a topic that we've been working on for some time here at Conserve, and I'm going to discuss integrating Haystack systems and using MQTT, which is a technology some of you will be familiar with, but also a newer technology that works together with MQTT called Sparkplug. So today, when we integrate our systems, there can be some challenges in integrating between different Haystack devices or applications. And so it can be time consuming and it can be difficult in some cases. Another problem we have with integrating Haystack systems is that we don't have a single source of truth for tags. Sometimes tags are in the BAS, sometimes they are in a device, and often they are in a cloud application, whether that be analytics or visualization. And maintaining the accuracy of tags over the lifetime of a system can be tricky, depending on where we put our tags. And so often tags are put into the cloud or the analytics or the visualization application, but this makes it difficult to maintain tags when the real world changes. So when a site changes, when a new device is added or a device is removed, a piece of equipment is changed. These are real world situations that need to be handled in the integration of Haystack systems, whether it be tags or tags and data. And often in our integrations, we need to compromise cybersecurity by opening TCP ports in firewalls and other strategies as well. And this cybersecurity is a very important aspect of integrating systems across the internet to the cloud or even internally on private networks. It's still very important. So today we have this particular challenge. Oops, sorry. So currently when we integrate Haystack systems, we do have a few ways of doing it. Project Haystack has a very well-defined REST API, which is documented on our website. There's a Java reference implementation that exists. We have open source implementations in Niagara. There are other open source libraries available as well to assist with integration. We have commercial products that implement the defined REST API. But typically, we do integrate Haystack systems either using BACnet or Modbus or using HTTP transfers using the REST API. These methods work. They can deliver results for customers, and they are really the status quo of the industry today. This is how we deliver integration for Haystack systems. But they do have some challenges. They don't scale well, so they're very difficult to transfer large amounts of data across the internet. They are not necessarily secure, although cybersecurity is always a changing landscape and new developments are occurring. And these are not necessarily suited to high volume, highly scalable IoT applications. And so really what we need to do is look for other ways of integrating our Haystack systems. I did say that we do use REST as a mechanism over HTTP for integrating our systems. And there are a number of cases, I imagine, where using this model is useful. But there are disadvantages of REST when we do start to scale up and do start to transfer data across the internet. Firstly, HTTP is a pull model. So we have to use a request response mechanism to get data out of our systems. And this means we have to think about cybersecurity, and security is always difficult to implement and it involves many, many people. The payloads in HTTP are not, or REST API are not automatically suited to IoT. IoT devices really only want to transfer small amounts of data. REST and HTTP are suited for larger text payloads. And so whilst we can compress them on the fly, this adds overhead to CPU and to our CPU, and we don't want to add overhead on our CPU to constrained devices. There is no standard authentication mechanism for REST. And so this means it must be implemented differently for each application. Haystack does define the SCRAM authentication, but different web servers, different applications will still have different requirements. And by definition, REST uses HTTP. HTTP allows for non-standard or customized payloads. The Haystack REST API is well defined, but still out in broader industry, there is no clear standard. So how can we make this easier? There needs to be a solution for some of these challenges. And so the first one is we need to have a single source of truth. So we need to be tagging at the edge, and to tag at the edge allows us to do a lot more in solving these problems. What we also need is, rather than having to ask a system or ask a remote device, when are you there and do you have any data for me? We need sites and equipment to announce themselves to applications. We need them to say, I am here, I'm ready to transfer data, and here is all the tags about me. We also need our tag databases in the cloud or in our applications to be built automatically. We want to reduce the human labor. So application tag databases need to be built automatically. We also would like to use a push model to transport tags and data to applications. We don't want to have to request or pull data out of systems. We really want to be able to have our remote systems push up to our applications. And what we also want to do is we want to use binary encoded payloads that reduce the amount of data we're sending, but we don't want to have to use compression. So we want to have open source standard mechanisms of encoding our payloads that reduce the size of the payloads that we are going to send. And so there's a few ways we can do this. We can bring some existing components, open source components together to help solve this problem. One of those components is MQTT. It's a well-known IoT protocol. Many of you will be familiar with it. It's lightweight, it's publish, subscribe. It's great for connecting remote devices that are small or constrained, have minimal bandwidth. And so, MQTT is a great way to start to solve this problem. It's due to its scalability, and also the open source solutions that are available through the Eclipse Foundation, but also through other agencies as well. Another component we can use is Sparkplug. Sparkplug is a relatively new specification that works in conjunction with MQTT. And this is now starting to gain traction in the industrial IoT space, and I'm hoping we can start to see some applications of Sparkplug in the buildings IoT space. So Sparkplug is an open source software specification, provides clients a framework to integrate data from applications and sensors. And Sparkplug really seeks to solve a problem with MQTT. MQTT is great, but every MQTT implementation is customized. The topic namespaces are customized. The payloads are customized. State management doesn't really get implemented very well. So Sparkplug solves these things, these three areas. It defines a standard topic namespace, which we'll see in a minute. It defines exactly how we can do state management. So are our devices online or offline? And we have a very well-defined payload that is binary encoded. So the key features of Sparkplug is it allows us to have a single source of truth in our remote devices. So we can configure everything at the edge one time only, and we can rely on that as well because Sparkplug can transfer all of our data. We can decouple our data, so we don't need to have direct connections into our systems. We can use a broker, MQTT broker, to act as that decoupling mechanism between our sources and our sinks of data. Devices and systems are immediately discoverable by mechanisms built into Sparkplug that allow systems and devices to announce themselves to the applications, and the applications will then know that they are available. Security is built into Sparkplug because we inherit the security features of MQTT, which leverages TLS encryption, both server-side and client-side, for enhanced secure connections. And then we talk about this state awareness, so we know when devices come online or offline. So I'd just like to give a bit of a brief overview of Sparkplug. It's probably a new technology to a number of you in the Haystack community. Whilst many of you would be familiar with MQTT and the idea of publish and subscribe mechanisms, Sparkplug is new. So we have this idea of an edge of network node, and a node would represent the gateway to a site or a group of devices. And the edge of network node speaks Sparkplug using MQTT. A device or a Sparkplug device sits behind a node, and that device cannot speak Sparkplug. So it needs the edge of network node to connect up to our applications. We would need an MQTT broker, which is the way the messages are distributed around to the various devices and applications. And a broker acts as that central distribution component for all of the messages that are published and then distributing those messages to be subscribed. We do need a certain version. MQTT 3.1.1 needs to be supported at a minimum, and so that's very important. We also have our application nodes, and these nodes are applications that participate in our Sparkplug system and help produce and consume messages. And so they will be, there are some examples of some applications that we can talk about. We have this idea of the node birth. So we have our edge of network node that acts as our gateway to a building or to a system. And so the node birth is when the node comes online and it announces itself and says, I'm here and I'm ready to go. And it publishes a message to a specific MQTT topic saying, I am online. Likewise, we have the device birth. So when a device comes online, it notifies its local node. The node publishes a message to a device birth topic, and then the system knows that a device has come online. Conversely, we also have the idea of a node dying or going offline, and we also have this idea of a device dying and going offline. And all of these mechanisms are handled using standard, well-defined MQTT topics that are documented in the Sparkplug specification. So what are these topics? So let's just quickly look at our Sparkplug topics. And if we look at a standard MQTT or a regular MQTT implementation, we can see that we would have topic names of various configurations. So here I could define an MQTT topic as Project Haystack Conf Device 1 Temp Value, or Conserve at Australia Melbourne Lab Controller Digital Output 1. This is what typically people do with MQTT. In the Sparkplug specification, they define a very well structured set of topics that are used, and these are the only topics that can be used. However, you can accomplish absolutely everything we're going to discuss today using these topics. These topics enable state management, so online, offline. They enable publishing of data. They enable subscribing to commands. And we can identify individual systems, nodes and devices by configuring this group ID, the node ID, and the device ID. And so this is how we can configure everything in our system to talk to each other. And so we end up with a system architecture looking something like this. In the middle, we have our MQTT broker, which acts as the central data or message distribution mechanism. We have a bunch of MQTT application nodes. So these would be other applications that are interested in the data in our system. We might have a primary application, which could be a web supervisor or a Sparkplug enabled host. And then we have a whole range of JS8000s or other devices which act as our gateways or edge of network nodes. And then behind our edge of network nodes, we have our devices and sensors that don't speak Sparkplug. And so by using Sparkplug, we can integrate all of these things in a very seamless way using open standards and leveraging open source software. However, there is one key concept I haven't talked about, and that's the payloads. Sparkplug payloads are fantastic. They are very well defined, formally defined data structures, encapsulates around 20 different data types and ways of encoding the message. The payloads are built and encoded using the open source libraries from Google protobufs, and they're encoded into a binary payload that automatically reduces the size of the messages we are sending. Payloads are designed for constrained devices, and the payloads can carry point data, so live point data. They can carry trend logs or time series data, but most importantly, which is perhaps the point of our discussion today, they can carry metadata. Sparkplug can transport Project Haystack metadata and tags in the standard messages. And we can leverage MQTT and Sparkplug to enable self-building applications. So now it is absolutely feasible to tag all of our devices and equipment and build our semantic models right at the edge in the BMS or the BAS or whatever we have on site. And then using Sparkplug and MQTT, we can automatically push all of this metadata up to our cloud application, and we can automatically, securely, and efficiently build our applications, totally minimizing the use of human labor. And so this is one of the key takeaways from today, is that we can automatically push metadata up to our cloud applications to be consumed just as any other Haystack data would be. So a couple of key concepts just to summarize. Our edge of network node would be the sort of the site level in our Haystack terminology, so the head end or a web supervisor. A device Could be a zone control, an area control. It could be a piece of equipment, so an air handler, a VAV, or a chiller. And so we would tag this as an equip with all of the appropriate tags. The birth and death concepts of devices are synonymous with our device ping, so a device coming online or offline. One thing I haven't mentioned is this Sparkplug concept of a metric. A metric is exactly the same as something we would see in Niagara, for example, as a control point or a data point. And in Haystack terminology, we would tag that as a point with all of the appropriate tags for each of those points being applied. We can transport data sets. So a data set in Sparkplug is the same as a trend log or time series data. And again, the most important one in Sparkplug are our property sets. And our property sets are name value pairs. And we call those tags. And so we can transport sets of tags or lists of tags up to our cloud application. Bit of a technology comparison. I won't go through too much of it, but here's just putting the idea of Sparkplug and MQTT side by side with the use of a REST API and HTTP. I want to highlight a couple of key points. So publish, subscribe for Sparkplug versus request response for HTTP and REST. The security aspects of configuring Sparkplug and MQTT versus the REST API. Standardized and binary encoded payloads again versus the payloads in HTTP, which have to be zipped on the fly. And also the authentication mechanisms are very good to compare. In REST and HTTP, we have no standard auth mechanism, but in Sparkplug and MQTT, we have these things baked in as well. And Sparkplug and MQTT are designed for IoT and constrained devices. And this is very key, whereas HTTP is designed before the IoT took off, and it was meant for powerful web servers. And we need to take this into account. So let's walk through a simple data flow of how this might work in practice. And so here on my screen, here in the presentation, we have a number of the key components. I've defined an edge of network node. I have a device. I have my broker. I have an application that I've written or that we've defined as our Haystack application. Right at the back behind all of this, we have a Haystack tag database. And then we have the user aspect of this, which might be a web server serving up a user application to consume all of this data. So in the first step, when our node comes online, it's going to publish to its end birth topic or its birth message announcing that it is online. And it's going to send all of the tags for the node or for the site level. And so that's what is going to be sent up to the broker. The broker will distribute that message down to our Haystack application. And the Haystack application subscribes to the birth topic and it receives that message from the node. Then our application will go through that message. It will parse out all of the tags it has received, and it will create an entity in our Haystack tag database. And so here we have our tag database being automatically updated using open source components and building our application as we go. And this allows us to preserve a single source of truth at the edge. So if anything changes here, these can be pushed up and the changes are automatically propagated into our Haystack tag database. Sometime later, our device comes online and it tells our node. Our node will then publish a device birth message on the device birth topic. The broker will distribute that again to our application because it's subscribed to that debirth topic. And our application, again, will look at the device, it will look at the points that the device is pushing up, and it will take all of those entities and create the entities in our Haystack tag database. And so now what we've done is enable an entire data flow in the system using these open source open standard components to automatically build a tag database. Once we've built our tag database, then our application can automatically consume that data that we've built. And so here what we've been able to do is to deliver an automatically built application, minimizing human labor, preserving our single source of truth, and enabling updates at the edge of our tags, and reducing the overhead of integrating our systems, achieving this in a secure manner, of course. So here's a list of what we've achieved. I've just talked about all this, but I think the overarching takeaway is that by working in this way, by announcing that nodes and devices are online, by pushing tags up automatically building our tag database, what we've been able to do is deliver a powerful, secure, scalable platform for building apps and applications in the cloud, whether it's visualization or analytics or a mobile or cellular phone system application. These are, reducing the labor involved in this is really important. Being able to do all of this automatically is absolutely super important as well. So what I would like to do today in way of a demonstration is introduce to you a Haystack Cloud reference design. And this is something we've been working on at Conserve using all of these components. So everything I've talked about today isn't just a nice discussion. There are actually practical software components behind all of this. And so today I'm going to do a quick demonstration of how this works. So on my laptop here in a minute, I'm going to show you a broker starting up, so a Mosquito MQTT broker starting up. We have an application which is going to be simulating, a cloud application. It has a Sparkplug client in there, so it can consume Sparkplug messages. It has a web server which implements a REST API, and is also serving up a user application. And this user application, we've managed to make a very simple one to show a tag database being built. And this uses the fantastic work from Gareth Johnson and J2 Innovations with the new Haystack React library, the Haystack End Client library, and the Haystack Core library that they just released last week. And so we jumped on that and thought we'd use that to those libraries to help build our very simple, very simple application. But the most important thing is we have this Haystack tag database. And so we've just developed a very simple in-memory tag database as a proof of concept for this cloud reference design. And in order to see all of this working, we've also developed a node simulator, so an edge of network node simulator that has a number of devices being simulated at the same time. So, so we can see all of this running. We can see our broker running. We can see our application running. We can see our application with the Sparkplug client and the tag database being built. And we'll see our simulators being running as well. So if we just hop out of our presentation for a minute and start to load up our demonstration. So the first thing we're going to do is start our broker. So here we now have very simply an MQTT broker being started up. So that's now ready and waiting for clients to subscribe. We'll have our application that we talked about, and so we're just running our application. This is now starting up a web server, and I can see my application being served over here in the web browser. This application has a tag database behind it, but at the minute there is nothing in my tag database. If I do a quick search, we can see that there is nothing there. So what I want to do now is start up one of my simulators. And so I'm going to do that right now. And we'll see that things start to happen. And so right now, my simulator is sending up information to the tag database. And I can see that some entities have already come up in my tag database. And I can search this to see what entities I've got. I've got a site. I can have some AHUs, and so you can see at the minute we have 2 AHUs, and every few seconds, if I do another search, now I have 3 AHUs. So we can see now that my node simulator is sending up information from itself, from the devices that are also attached to it, and we can see that my tag database is also being built up. If I now start a second node simulator, so or a second site, then we'll see straight away that if I query the sites, I now have 2 sites. So now straight away by connecting another node, I can see that there are more than one site. And also likewise, I can see that I've got air handlers now from my Office 2, so my second node, and I've got air handlers being built and added into Office 1 at the same time. And just to prove that it works with more than 2, we can start a third one, and we can see that now my tag database is definitely growing. I've added a site. So Haystack HQ is now part of our tag database that's being built. And we can see many more air handling equipment is being added. I know this is a lot and we move very fast, but what this is a demonstration of is that we can automatically build our tag databases through using MQTT and Sparkplug mechanisms to push data up, and we can consume that data as well at the same time. So very quickly, I need to wrap up. I think I'm about to reach my time limit. I'm thanking you very much for your attention. If we just finish up, the next steps for our Haystack Cloud reference design, we'll be looking to open source this shortly. I did announce this design in the Haystack Connections magazine at the end of last year. We will be open sourcing this and making all of these components available for the community to use and to play with. We'll be looking to keep this reference design up to date with open source technologies, the MQTT brokers, the Paho client, the Tahoe Sparkplug implementations. These things are continually evolving and updating. And so we'll be keeping this technology up to date with that. And we're investigating potentially a community hosted or public instance of the Haystack Cloud reference design for people to use and to test and to play with as well. There are a number of resources online. There's some links here. I'm sure the presentations are going to be made available for everyone, as will this recording be. So you can quickly, if you want to learn more about Sparkplug, you can just go into any of these, or Sparkplug or MQTT. You can go into these presentations, so these links, and learn a lot more. And lastly, if this is something that you are interested in, if you would like to explore it more, please get in touch. Conserve is developing this technology. It's developing more solutions based on Sparkplug. We're actually deploying Sparkplug in a commercial application. So we've developed a Niagara Sparkplug integration that already does everything that's been demonstrated today. And this is something that we will be building out and building more of, and deploying more systems that use this technology. So thank you very much. This has come to the end of my presentation. It's amazing where 25 minutes goes. I appreciate everyone who has stayed around to the very end of the Haystack Connect conference. I trust everyone enjoyed themselves, they learned something, and they are keen to get involved and continue to expand and grow the Project Haystack world and community. Thank you very much. I look forward to seeing you all soon.